Welcome everybody to the second webinar of our MCS CIG CSDMS webinar series on the role of computational geosciences in the predictive assessment of plate boundary systems and hazards. We got together as these three community organizations to discuss what best practices are and what some of the challenges are in terms of combining computational approaches with physical models to understand what is happening in a sense that is helpful for assessing hazard of both naturally induced seismicity in the case of this week and human-induced seismicity. Yesterday, we had a great talk by Jim Dietrich and an introduction by Kayla Kroll, which will be archived at our MCS RCN website later, and you will be able to access that. Today's seminar will focus more on the high-performance computing aspects of this problem. We'll be having two presentations followed by a period of questions and answers, so please make use of the question and answer feature. And please note that this webinar will be recorded. I'll be handing over, I'm Torsten Becker, and I'll be handing over to my colleague, Alice Gabriel, who will be introducing today's speakers.
Thank you, Torsten. Welcome everybody also from me. It's my pleasure to welcome today two excellent speakers talking to us about modeling induced seismicity in the high-performance, using high-performance computing infrastructure. So we will have first a 10-minute introduction by Josh White, followed by a half-an-hour talk by Kayla. And Josh is a group leader at Lawrence Livermore National Lab. He gained his undergrad from Princeton and his master's and PhD from Stanford. And his research focus is now focusing on integrating monitoring techniques with large-scale computing to improve our understanding of complex geologic systems. And Kayla, on the other hand, gained her master's and PhD from Riverside and joined afterwards Lawrence Livermore, and she's really focusing on induced seismicity, fault interaction, numerical earthquake simulation, methods to estimate the state of stress in the subsurface related to seismic hazard, geomechanics, and machine learning applications for the subsurface. And I'm really excited to hear the modern approaches after the great introduction yesterday about kind of the history and the state of the art of physics-based earthquake modeling, and hand over to Josh.
Great. Well, thank you very much for this kind introduction. And it's really great to be able to present to this community. Let me pull my slides up. Everyone can see that?
Perfect.
Perfect. Great. Yeah, so the organization for today, I'm going to speak for about half time, 20 minutes, and then Kayla is going to go after me. We thought it would be good to give an introduction to sort of the current state of the art for numerical methods for reservoir simulation and reservoir geomechanics. So these are kind of long time scale, quasi-static processes that I'll talk a little bit about. And so, for example, here, in fact, this is if you're wondering what this is actually a reservoir simulation of a faulted field. And there's an injection well, which you can't see here, which is generating, these are actually fluid pressure contours, generating fluid pressure in a fault-bounded system. So these are actually faults here. And so perturbing the state of stress on these faults. So I'm going to talk a little bit about how we actually simulate fluid flow and geomechanics. Kayla will then talk more specifically about how we actually then address the potential for induced seismicity on large structures like this, or maybe smaller structures that we're not aware of. So I will talk a little bit about the governing equations, try to give you a sense for the numerical methods that we use, and a few of the computational challenges. Tomorrow, then, I will go a little bit into sort of the future of computing as we move into the exascale age, and maybe where there's some kind of numerical challenges that could really have a dramatic impact on the induced seismicity and general reservoir scale problems. So just to maybe orient you, and for those who weren't able to join yesterday, So we're interested in typically kind of subsurface injection operations. And so as a good example here, I've picked a cartoon of a carbon capture and storage operation. And so the idea is that we have some point source of CO2 from which we capture maybe a pure CO2 stream. Most often in the public's mind, they think about capturing CO2 from power plants, natural gas power plants, coal power plants. In fact, in the near future, most likely sources will be industrial processes, cement factories, steel factories, refineries. A huge sector of our economy actually produces relatively pure streams of CO2 that are easy to capture that normally might be emitted to the atmosphere. So we capture that CO2, we transport it, by pipeline, usually to an injection well. We then inject it into a deep subsurface formation. So most CO2 reservoirs are deeper than, all of them are deeper than 800 meters, and they're typically more like 2 kilometers underground. But now, this is a porous system, and so it's very much like a sponge. It's very much like your kitchen sponge. As we inject fluid, we increase pore fluid pressures, and this whole system can deform and respond poroelastically, or even with more complicated geomechanical mechanisms. So here we see, as we inject, we have a CO2 plume that's actually moving away from the well. That CO2 plume is displacing in situ brine. And so then that brine also will kind of move away from the well, creating a pressure plume. And the concern is that, and then there's a third concern. We think about actually 4 plumes. CO2 is quite cold. So there's actually a thermal perturbation immediately adjacent to the well, but usually it's quite small. We then have the CO2 plume, which goes further from the well. We then have the perturbed pore pressure volume. So the volume of fluids that are actually perturbed because of the increase in pore pressure, and that's even larger. And then even larger than that, we have the far field sort of poroelastic volume, the volume of rock that is undergoing stress changes. And that can actually extend quite far from the well. And the concern is that changing effective stress conditions in the subsurface could, for example, change the normal effective tractions acting on faults and allow them to reactivate either quasi-statically or potentially, rupturing dynamically and releasing earthquakes and seismic energy. In practice, we're interested in a whole bunch of other geomechanical effects as well. Many reservoirs, for example, have stress-dependent permeability. If we inject at too high pressure, we may induce hydraulic fracturing. Even if there aren't large faults in the reservoir, small fractures and highly fractured systems, we can actually reactivate them with hydraulic shearing and so forth. Okay, so that was a cartoon, just to maybe give a real field life illustration of how important these sort of geomechanical and poroelastic effects can be. These are actually 2 figures from the Insala CCS project. So this was a large-scale onshore CCS project that took place in Algeria between 2004 and 2011. Insala is a gas field, so we're actually looking here at a plan view of the reservoir. Each of these black dots is a production or injection well. The ones that have like a strike here, these are actually horizontal wells. At Insala, it's a gas field. So what they're doing is these wells were producing natural gas, but that natural gas had a very high CO2 content. And so they would remove the CO2 and re-inject it into the reservoir, into what we call the water limbs of the reservoir, through these wells 503, 502, and 501. And in doing so, they built up pressure in the reservoir. What's interesting about Insala is they actually used a satellite-based surface deformation monitoring technology. So basically using a satellite that repeatedly passes over the site and shoots a radar survey, they could actually measure the uplift or subsidence of the ground due to injection at about 2 kilometers below the earth. And so that's actually what we're seeing here. So this color bar here, range change. This means the movement towards or away from the satellite, but you can really think about it as uplift. And what we saw was immediately above the injectors, there was uplift of about 2.5 centimeters. So we see quite substantial, I mean, no one at the surface would be able to detect it. It's quite small, but certainly measurable surface deformation well above the injection well. Okay, so here we're interested in sort of simulating these systems. You know, how does complicated fluid flow and rock deformation interact with one another? I will say that reservoir applications, though, it's an exciting area to work, but a challenging one because it tends to hit many of the weak spots of classical numerical methods. And I'll highlight a few here. The first one is we often have a mix of what I'll describe as continuum and discrete behavior. You know, we're often modeling, you know, 3D partial differential equations describing a 3D volume, but then we'll have different equations describing surfaces embedded in that volume. Things like fractures. So on the right here, you can see this is a highly fractured shale, faults again. And so we have this mix of sort of, you know, discrete features, 2D surfaces, and 3D volumes that we need to address. The second one is that these systems are very much multi-scale. And in many cases, we actually have poor scale separation. And so, again, maybe looking at this figure here on the right, you can imagine these fractures here have a very important control on the fluid flow in fractured reservoirs. But we know, for example, that faults and fractures exist at basically all scales in the subsurface. They tend to follow, you know, a power law distribution and scale. And oftentimes we need to make a pretty arbitrary choice about at what scale will we explicitly resolve features on the grid? You know, which faults will, you know, bigger faults, we say we can explicitly model them on the grid. But then at some point, it's intractable to put small features like these fractures. And so we need to introduce an artificial scale separation. And how do we do that well? The same thing occurs in time. You know, many reservoirs operate for 10 years, 20 years, 50 years, very, very long time scales. And it's not unusual in our reservoir simulations for the typical time step to be a day or a week or you know, 20 days or a month, you know, when you get to steady state. So we're taking these very, very long, quasi-steady behavior time steps. But then if you think about an earthquake rupture, I mean, that process evolves over seconds, you know, maybe time steps of milliseconds in dynamic rupture simulators. And so how do we bridge this gap of very slow scale forcing changes and then very sudden ruptures? These systems are multi-physics. You know, we need to think about multi-phase flow, elastic and potentially plastic or viscoplastic deformation. Thermal effects are very important in some systems. Certainly the earthquake nucleation and rupture process is very, very complicated. And whenever possible, we look for weak couplings that we can exploit, but for many physical processes, these couplings are quite tight, and therefore we need to model these processes simultaneously. And lastly, these systems are very nonlinear, which can be very challenging for nonlinear solvers. They often enforce small time steps, which increase the computational cost and so forth. Yeah, so there's all these challenges, but we don't give up because they're very, very strong economic and environmental drivers to actually have better modeling tools to support decision-making. And so this seminar series I really love it because it's getting directly to that question of how do we provide better tools to support better sort of hazard assessments and risk assessments. Okay, so to maybe fix ideas, just to give you a sense of the types of equations we solve and put into our numerical models. I'm going to begin with a relatively simple system, but it does illustrate, I think, a lot of the complexity you will see in more complicated models. And so this is multi-phase pore mechanics. So forget for the moment about faults. We're really just focused on the porous rock itself. We basically have three primary quantities of interest that we want to get at. The first is a displacement vector, U, a field of displacements. So we have a porous rock, so we want to think about how that porous rock sort of deforms and displaces. Then we're going to look at a model where we actually have two phases in the pore space. And I've just chosen oil and water. So this is a simple two-phase model where we say we have these two phases. In this model, we think that they're immiscible, so they will remain as separate phases, but they will co-occupy the pore space. And so we use a mixture model. We don't directly resolve, for example, the interface between oil and water. Instead, we think about the saturation of water in the pore space. You know, that 50% of the pore space has water, 50% has oil, and over here it's 100% water, and so forth. And then the last thing is we have a fluid pressure. And in this model, I've assumed that there's no capillary effects, and therefore the fluid pressure in the water and the oil phases is identical. Okay, so we have three primary variables. We then need three governing equations. And so the governing equations we will have will be a linear momentum balance, okay? And so this is going to relate the effective stress, sigma prime, basically the stress in the solid skeleton of the rock, with the pore fluid pressure. B here is what's called BO's coefficient. It's a measure of how strongly pressure and skeleton stresses kind of couple together. So we have this thing. Then we have body forces due to the density of this whole mixture and gravity, okay? So that's our sort of linear momentum balance. We then have a mass balance equation for each of the phases. And so really this contains two types of terms. There's what we call the storage term. So this is really measuring how much fluid mass for that phase is in the pore space. And so it depends on the density of the phase, the saturation of the phase, and then the porosity. And the key point is this porosity, because we have a deformable medium, is actually changing. The porosity is a function of the displacement field. And so you can see immediately that these equations are starting to couple together. And then, so we have the storage of fluid in the pore space, but then we also actually have that fluid can flow in and out of a volume. And so we have, for example, the phase velocity VW, the velocity of the fluid phase flowing in the system. And then we have an identical equation for the oil mass balance. We then supplement these with constitutive laws and closure laws. So for example, we need to relate the effective stress to the displacement field. And so we'll do that using some sort of solid constitutive relationship. The obvious one is linear elasticity, but in many systems, we actually have plastic behavior. We then need to relate, for example, the phase velocity to the fluid pressure P. And so for that, we'll use a generalized Darcy's law. And then we need to relate, for example, how does the porosity change with the solid deformation? And so that appears through the volumetric strain, which is a function of the displacement, and also through a direct coupling with the pore fluid pressure. So if you're interested, this is a pretty standard system, and I can point you to references that really go into details about how all of these things couple together. But the key point is that we have a nonlinear system of equations, relatively complicated constitutive equations, and so forth. Now, this is a pretty standard system, but you can imagine there's a few ways that this can get simpler or more complicated. If we're just interested in a single phase system, so for example, let's say water disposal, where we're injecting water into water, then in fact, we can get rid of the oil mass balance equation. This saturation is 100%, this will simplify. So we get a simplified set of equations. In many systems, we have more complicated phase behavior. So for example, in that CO2 system, we have CO2 and water. The CO2 can actually mix with the water, so we end up with what we call a compositional flow formulation. It has a similar structure, but is a little bit more complicated. Okay, so this is just for the bulk of the rock. We also have injection wells, which serve as sort of a boundary condition for the system. In fact, to model those well, we often model them explicitly with their own partial differential equations discretized along kind of the 1D trajectory of that well. And so we actually have mass balance equations for the fluid flowing in that well, tightly coupled with the reservoir. So that's an additional complication. And then you can imagine if you have a fault, then we have, we have our volumetric problem, but then we actually have a contact problem being forced at the fault. We need to enforce some sort of contact constitutive behavior. And that can be done in a few ways. The simplest way is through sort of quasi-static Coulomb friction. But if you really want to model earthquake ruptures, then we need to be more sophisticated than that. And Kayla will talk about that in some detail coming up. Okay, so those are kind of the typical governing equations. In terms of a discretization, I can think of at least 10 good ways to discretize this system of equations. It's a very active area of research. What are good discretization strategies? I'll show you one, which is a pretty typical one, and probably the most commonly used in practice, but there are certainly others. So the key thing is that because these processes are relatively slow in time, we tend to use implicit time integration. Okay, so we're going to come up with a system of algebraic nonlinear residual equations. Okay, and those consist of 3 residual equations: one for the momentum balance, one for the wetting phase mass balance, and one for the non-wetting phase or the oil mass balance. And so we create a grid. Typically, the displacement field, we will use a continuous Galerkin finite element method. So we will have displacement degrees of freedom located at the nodes. And so the momentum balance equation is really thought of as a sort of a finite element scheme for the momentum balance equation. For the mass balance equation, it's widely preferred actually to use finite volume schemes because of mass conservation properties and some other features. And so we will typically have pressures and saturation as cell-centered variables in the center, piecewise constant interpolation of these values in the centers of cells. And then we compute numerical fluxes, sort of relating mass that's interchanged between these 2 cells. And so this is a typical discretization. One challenge with that one is it's not an intrinsically inf-sup stable discretization. For those of you who are finite element experts, in certain regimes, we can actually run into a stability restriction. And so we usually add an inf-sup stabilization to the system. So we will often use a macro element concept, but there's a variety of ways to stabilize it. Here I've drawn sort of a Cartesian mesh, but there really is no restriction. We typically work on fully unstructured meshes with tets and hexes and wedges and so forth. So we end up with a series of residual equations. Like I said, we use implicit time stepping. So we will use something like Newton's method to solve this system of equations, which means we have to solve a linearized set of equations and basically solve, to advance the solution in time, a very large system of matrix equations, linear algebraic equations that look something like this. So this is a sparse matrix. This is a big sparse matrix. Because we have 3 fields, we tend to think of it as having a partitioning into like a 3x3 block structure. This AUU matrix here, for example, is the coupling between displacements and displacements. It's basically an elasticity matrix. So if you did a standard finite element discretization of elasticity, you would end up with this matrix. But because we have coupling with other physics, we end up with a much larger system of equations that we need to solve. Okay, so just to give you kind of a visualization, a toy to see exactly how all these equations come together. This is a toy example, I think, that nicely illustrates it. No real field really looks like this, but it's a fun example. Imagine we have a cube. We inject water into one corner of the cube, and we produce water from another corner of the cube. It then has this kind of layer cake structure where we have high permeability layers, but which are also stiff. And interbedded with them, we have low perm and soft layers. And then the reason we call it a chimney model is these layers are actually connected by little chimneys here and there. And so if you actually simulate this, then you end up with a numerical solution after about 50 days that looks like this. So like I said, we're injecting water through a well here. And so here you can see the water saturation. So there's a plume of water, which is displacing the oil, which is sort of hidden here. But this plume, when it reaches a chimney, actually, excuse me, migrates up the chimney, and then it gradually migrates up the whole system. At the same time, we're generating overpressure in the system. So this is a plot of the overpressures in that cube. And so you can see a distinct effect from the layering and the properties. And then the whole cube itself is actually deforming. And so when, the whole thing's kind of uplifting, but in fact, in the top layers where we're producing fluids, it's actually shrinking and so forth. And we get, so you can see one immediate challenge that may be apparent from this, from a numerical point of view, is that we have both what we call elliptic or parabolic type behavior, global scale interactions, but then we also have sort of sharp fronts, kind of hyperbolic type behavior where we've got fluids being transported in the flow fields and so forth, and we need to be able to resolve these sorts of fronts well. Okay, so that's a toy model. There was a lot of discussion yesterday about sort of how do we characterize and sort of, have good certainty about what the real field looks like. So I thought I'd show you sort of a real field example, how we build one of these models. This is, I'm going to show you a model that we built for a site. It's being looked at as a potential storage site for CO2. In the offshore state waters of Texas. So as you may know, the Gulf of Mexico is a huge oil and gas producing region, but it actually has a huge capacity for CO2 storage. Current estimates are that it could store something like 125 gigatons of CO2 in this coastal region of Texas and certainly continuing into Louisiana. A huge potential storage resource. And so we've been looking at a particular storage target here called High Island. This is a cross-sectional view through the stratigraphy that we're looking at. And so the storage target is in this lower Miocene formation. So the Gulf of Mexico has these very thick sandstone units. So very high porosity, very high permeability, very large potential for storing CO2. It's then overlain by these caprock units, which would do a good job trapping CO2. But the Gulf of Mexico is highly faulted. Now, these faults are these large offset faults we know are actually good seals. They're impermeable, but they do complicate the geometry of the systems that we need to model. And one advantage of the Gulf of Mexico is because there are literally thousands of wells out there, from each well, we have lots of logs. So we have a really good understanding of the lithology, porosity, permeability, for some wells, sonic logs, and elastic behavior. And then we also have a variety of what's called active seismic surveys. So these are remote geophysical surveys that give us a good sense of what the layered structure of the Earth really looks like. So when we build one of these models, we begin with all that seismic and well data to build what we call a structural model. So that really identifies the horizons, the faults, and so forth. So we create a volume like this. We then need to mesh it. And so here I'm showing a tetrahedral mesh that conforms to those fault surfaces. What's probably immediately apparent is that real fault geometries are complicated. This has 21 faults, which are intersecting in very complicated ways. Therefore, building meshes that actually conform to this fault geometry can be very challenging. In traditional reservoir simulation, when they're just interested in fluid flow, frequently they will build grids that don't necessarily perfectly honor the geometry of these faults. They'll kind of stair step around the faults. But when we do mechanics, because we're interested in an understanding of the tractions and the stresses on these faults, we're really obligated to have a good conforming grid to these faults. And so that can dramatically complicate the meshing challenge. Okay, Then once we have that grid, we populate it with wells, so we have various wells, injection wells, observation wells, and so forth. We typically break into different units, overburden, shale, sandstone, and so forth. We then populate it with properties. So the big ones we need to know are the porosity field, the permeability field, and the elastic moduli, so bulk modulus Poisson ratio. Obviously, at any given point in the reservoir, we really don't know what they are. So most frequently, we use geostatistical models. So we generate a stochastic realization of the field, but that is somehow constrained to observations in wells and so forth. And this is a whole process in and of itself of how we generate good sort of field data. But once we have that model, we can then run poromechanical simulations. And so here I'm showing where we're injecting, this is a plan view, so we're looking top down on the reservoir. We're injecting right into the top, into this hot spot right here, this red thing. Like I said, these faults are fairly offset, so we expect them to serve as seals. But we can, calculate, for example, the pressure buildup on this fault surface. And let's say in the far field, what the effective shear and normal tractions, how they may be evolving on these faults. And we can also look at remote deformations. For example, one question was, well, how much, if we injected, how much deformation might we see at the seabed, given that this is an offshore reservoir? And here we see, about 1 millimeter of uplift at the seabed. And then we go through typically a process. Okay, so that's kind of a forward model. We then have to go through a process of history matching to sort of calibrate it to observe data to get a model that we think is representative of what's going on. And then typically we'll do uncertainty quantification. There's lots of uncertain parameters. And so we need to really have a good understanding of how the uncertainties there might impact the performance of the field and so forth. We'll also forward model a variety of sort of monitoring observations we might have. So here I'm showing, for example, the response we would expect from a distributed strain sensor using downhole fiber optic. And so in this field, we would expect to see pretty large strains in the reservoir unit itself, but outside of the reservoir unit, relatively minor strains below the resolution of the fiber optic itself. Okay. So hopefully that gives you kind of a rough sense of the workflow and what the models really look like underneath. I will say that there are many computational bottlenecks. And tomorrow, we're going to go through quite a few of these, really talk about where are the real computational bottlenecks. And so I'll describe them. But here I'm showing just roughly kind of the loop that we go through. And in any one of these circles, I could give you 4 or 5 PhD topics. It's a rich area to be working in. Before I go, though, some people often ask, well, how big a model can you run in practice? What is reasonable using today's computational power? And so I'll give you one example. So this is a simple benchmark we use called the staircase benchmark. Again, no real field looks like this, but it does a good job really exercising the challenging elements of solving this type of system. And so we use this for weak scaling studies. So we'll start with a relatively coarse mesh, and we'll refine and we'll refine and refine so that we can generate larger and larger versions of this model. And so just to show you how that worked, we began with a model that had 680,000 degrees of freedom, and we ran it on 2 cores of one of our machines. And then we refined and we refined and we refined, and we add more cores. So this is a weak scaling study. But you can see that we can actually pretty handily run problems with hundreds of millions of degrees of freedom, and we can solve them in pretty reasonable times. So to do one time step here is taking about 30, 40 seconds. And then in a typical simulation, we have many, many time steps, but all of a sudden the whole simulation we can run on the order of hours, less than 12 hours, which is really our goal for sort of practical reservoir simulations. I will talk a lot tomorrow about how we're actually able to get here. This is not easy to get up to problems this large. And I'll talk a little bit about how we're hoping to get up into the billions pretty soon. But that's really where the computational challenge is. But at least for the moment, we can resolve quite large problems pretty handily. So with that, I will end, and I believe Kayla is gonna take over.
Okay, can everybody see my screen?
Definitely.
Okay, great. So Josh, thank you so much for that really great overview of the geomechanics. Yesterday, for those of you who were with us, Jim gave a really good overview of the numerical framework for the earthquake simulations as well. So now I will take those two things and talk about how we couple them together, and then show you a few examples of how we do it and what we can produce. Okay. Okay, so briefly, just to touch on the mechanisms again that are responsible for induced seismicity. First, we have these direct pore fluid pressure effects that arise due to the direct interaction between fluids and faults. And then we have these poroelastic stresses, which arise due to rock deformation. And as we just heard, the direct pore fluid pressure effects are dominant, as shown by this blue line in the near field, so up to a couple kilometers away from the fault. But these the direct pore fluid pressure effects really only affect the normal stress acting on the fault. Conversely, we have these poroelastic effects that are given by the red line that are dominant in the far field, but they act on both the shear and the normal stress components. They can be of either sign, which is important as well. One additional consideration is that there's also a time delay between injection of fluids and the onset of pressure along a fault, because fluids must be transported through the bulk. And so many authors have reported seeing this sort of diffusive behavior in the spatial temporal patterns of seismicity, where sort of you get this migration of seismicity with time, and they attribute that to fluid migration. Conversely, poroelastic stresses are transmitted nearly instantaneously. So as in this example for the Fairview, Oklahoma earthquake sequence, Thomas Goebel and others suggested that it was the poroelastic stresses that were responsible for triggering seismicity tens of kilometers away from an injection well, nearly just as soon as that well was turned on. Okay, so I wanted to point out these two mechanisms again, to basically say that today we're going to be focusing on the impact of the direct pore fluid pressure effects. But as Josh just mentioned, our current geomechanical codes are perfectly capable of capturing both effects, and the earthquake simulation is indeed capable of handling that as well. But to date, our goals really have been to fully understand the impact of the sort of near field dominant mechanisms before adding additional layers of complexity to the system. Okay, so next we wanted to have a look at the various ingredients or components that are needed to build a model in RSQSim. And so over the next couple of slides, I've highlighted properties in various colors. So red stands for the things that we either don't know or have limited data to support. And orange are the things that we think we know, or at least we can adequately approximate. And in green are the things that we think we're good at. So the first two requirements are reservoir characterization that's used to build a geomechanical simulation to produce external pore fluid pressure histories or poroelastic stress histories that we then use in the earthquake simulation. And I'm not going to go over this just because Josh just did a great job at that. So the next thing that we need is a fault model. And this fault model generally will come from geologic mapping or maybe lineations in microseismicity. We can also use things like 3D seismic data if, for example, the data are available and faults can be identified in it. But one caveat is that most of the induced events that we've seen to date, and even large tectonic events, have occurred on faults that we don't know about. And if we don't know about them, then they either get completely left out of the model or we have to approximate those features. And this would be the same thing for, say, a fracture network. So we may know like the general orientation of fracture sets, and we can include that in the model, or we would just randomly distribute fractures in a volume, something like a DFM. And in all cases, ideally, these would be the same structures that would be used in the geomechanical model, but there may be some situations where, due to meshing constraints, it may be easier to include faults in RSQSim, which is a boundary element code, versus to do the full finite element calculation on those fault structures. Next, we need some estimate of the rate and state constitutive properties. along the fault surfaces and the fractures. And we can usually get this from lab experiments. We can look to the literature for similar rock types. If we have a decent reservoir characterization, we might be able to take in situ rock samples, take those to an appropriately outfitted lab and conduct friction experiments on them to get in properties for in situ samples. Or even on a larger scale, if there's observed seismicity, we can fit this rate model that Jim introduced yesterday to the micro seismicity, and then we can back out some of these constitutive properties that way as well. The next thing we need is to have some idea of the tectonic driving stress. In seismically active areas, this is commonly done from GPS or geologic data, though they may not agree. But in poorly understood areas, this may be a challenge. So yesterday we saw an example where for the Valdagri oil field in Italy, they used RSQ-SIM to perform long-term simulations of tectonic seismicity and then history match that with observed seismicity to get some idea of what the long-term tectonic stressing rates might be. Or as I'll present here today, we may just neglect this property completely because induced seismicity often occurs in regions like crustal interiors that are relatively aseismic. And finally, we need some estimate of the pre-existing shear stress conditions on fault surfaces. And so this pre-stress field is a representation of the stresses that are on the fault surface that accumulate over a long time due to the interaction between things like tectonic stresses, fault roughness, and complex fault geometries, and then the stress changes from past earthquakes. So we can get an estimate of the stress orientation, at least, from regional stress maps, from borehole breakout and focal mechanism inversion data, for example. And then we can project those stress tensors onto fault surfaces. But at best, this is a smooth representation of the stress field, and we know that the stress field is inherently heterogeneous. So we can alternatively approximate that heterogeneity by using some stochastic distribution, but even then we don't know what the stress field looks like, so this is probably not accurate either. And then one question that's come up often is whether or not we can use earthquake sequences to tell us something about the distribution of stresses on a fault. And this, I think is very much an open question, but definitely one worth pursuing in the future. But for now, we're just going to employ a heterogeneous stress field that is stochastically generated using a von Karman autocorrelation function. And then we'll take all of these ingredients, items 1 through 5, and we'll throw them into our earthquake simulation code, RSQ-SIM. And just an example of some of the different types of stress field distributions that we can use. These are some face-on views of a fault surface. The stress conditions can vary from sort of short wavelength random fields that may be indicative of like a fresh or immature fracture surface or fault surface. And then they can also include these longer wavelength, more correlated fields that may be more reminiscent of mature faults that have hosted lots of slips. So say something like the San Andreas, for example. And then on the bottom row is just a different example of the kinds of patterns that you get that result from the same statistical properties. And here I'm just showing an example of the impact of the pre-stress field on rupture propagation. So on the top row here, we're showing the slip distribution from 2 earthquakes that occur at nearly the same time in their simulations, where the only thing that is different between these is the stress field distribution. In the left column, we see that the stress field is characterized by this sort of short wavelength random topography. And then on the right, we see that the stress field is characterized by this longer wavelength, more correlated topography. And we can clearly see that the stress impacts the shape of the rupture as noted in the slip distribution. So here the warmer colors indicate more slip. And then in the bottom row, there's a lot going on here, but the key takeaway is that the areas of red and purple, like this here and here, these are areas of above average shear stress. And then anything in cooler colors like these blues and greens here and here are lower stress barriers. And it turns out that these low stress barriers actually impede rupture and cause rupture to arrest, even though the overpressure on the fault surface is quite large elsewhere on the fault. Okay, and then just before getting into some of our other work, I wanted to make a quick note comparing the computational scaling between the geomechanical simulations that Josh just described, and then the earthquake simulations that we can do in RSQ-SIM. So with our current approaches for this sort of one-way coupling between the geomechanics and the earthquake simulations, the biggest bottleneck here computationally is by far the geomechanics. And we have the ability to do these really massive problems like Josh just described with 300 million degrees of freedom. But there are really two issues. And the first issue has to do with meshing regions of complex faults with finite elements, and that can be quite a challenge, as we've discussed. Whereas creating something similarly complex for RSQSIM takes a couple of minutes, say, maybe a little bit longer if you have lots of intersecting fault strands, but in principle, this only takes maybe a day or a couple days versus something that for full finite element model meshing can take months at worst. And the second thing that we see is for the largest problems with the geomechanical simulations, at least, they take about an order of magnitude longer or more computational resources than the largest of the earthquake simulations. So as a rule of thumb, the computational cost for the earthquake simulation with RSQSIM scales by the number of elements in the fault model. And then for, say, this example of a fault model with 100,000 elements, it may take a couple hours on a supercomputer. And so that's relatively fast for the kinds of things I'll talk about today. The models have about 60,000 fault elements and they run in 2 or 3 minutes. And so that's exceptionally fast. And so we can use these types of simulations then to perform thousands of simulations that sort of span the parameter space that we're interested in. So for example, since we really don't know the amplitude or the pattern of the pre-stress distribution, we can either model the impact of the stresses on seismicity by running a new geomechanical simulation every time, but that would take an eternity. Alternatively, we can model that behavior with RSQSIM and we can do tens of thousands of simulations in a matter of weeks. So that's sort of the approach that we're taking to date. And so now to move on to some case studies, we'll start with one related to the carbon storage community. So in that community, it's been suggested that we may be able to reduce the potential for induced earthquakes if we remove formation brines either before or during the injection of CO2. And then so you're specifically engineering the system to maintain this sort of net zero pressure change. And that may reduce the impact of seismicity. But there's, this is sort of a controversial topic. One, over the utility, and two, over the economic costs of such an endeavor. But our modeling approach at least allows us to explore the efficacy of this from a seismic perspective. So in this study, we injected fluids into a single injection well. And so this well is about 2 kilometers away from a fault that we're interested in. And it's buried at about 2.5 kilometers depth into a thin reservoir. We then co-produce fluids from one of 5 potential production well locations. And just to note, we only use 1 production well and the injection well in a single simulation. And we first wanted to see if seismicity could be controlled by injecting and extracting fluids in equal volumes. And if that works, then we're also interested in seeing if we can extract only maybe a fraction of the injected fluids, and if that would be successful, and also if that could be quantified. So real quickly, looking at some of the other ingredients that go into the model, as I mentioned before, on the top here, as a means of approximating a fault zone. In this study, we've employed something called a fractally segmented fault model. So in this case, we have a 5 by 10 kilometer fault surface, and it's discretized into 30-meter elements. And those elements are then grouped into individual segments like this pink one here. And those segments are offset from the strike of the fault. And the offset here is given by the color. And so both the offset then and the spatial distribution of the segment sizes obeys a fractal distribution. On the bottom left here, we're showing again another example of the pre-existing shear stresses that act on the fault surface. And finally, on the right, this is just a snapshot of what the overpressure distribution looks like on the fault surface in the middle of an injection operation. On this slide, we're showing an example of some of the synthetic seismicity catalogs that are produced by RSQSIM. So here we have the magnitude of individual events as a function of time during the injection operation. And then if I plot the magnitude frequency distribution For that catalog, it's given here, and we can see that we're reproducing reasonable statistics from these synthetic catalogs. Okay, and so in this slide, we're showing the primary results of this active pressure management study. Again, we performed thousands of simulations to investigate the efficacy of using active pressure management as a reservoir engineering strategy to reduce induced seismicity. And so in these figures, what we're showing is the total number of earthquakes in the simulations on the left column, and then the maximum magnitude in each simulation in the right column. And we choose these metrics because they are the primary components in a seismic hazard analysis. So in the top row, what we're showing is results from sets of simulations where we inject and produce equal parts CO2 and formation brine. And then in the bottom row, what we're showing is results from simulations where we only extract about 50% of the injection volume. So in this case, obviously the overpressures on the fault surface are going to be much higher than they are in these cases. Okay, and so then just real quickly, the colors in each panel represent a production well location, and there are some implications here for operational design, say, but for simplicity, let's just focus on sort of the average over all of the colors. We'll take a look at those results and comparing the top row to the bottom row. Oops. So here we can see for if we're willing to extract large volumes of formation brines, then we can reduce the number of earthquakes by say a factor of 10. And then we can also reduce the maximum magnitude earthquakes by about a whole magnitude unit here, but certainly less than or below maybe levels of felt seismicity. And so one of the other things to mention about this is that the impact of this type of pressure management approach is considerably sort of larger than if the other end member case, which is to not try to manage pressures at all and then just continue to inject at full volumes. Okay, and so next I'd like to revisit a topic that we talked about a little bit yesterday. So Jim showed this example of a complex pattern of seismicity that develops in response to oscillating or periodic injection or changes in injection rate. And so he did that with the simple or relatively simplified earthquake rate model, but here I'll show some examples of a similar problem comparing the results from a simulation with RSQSim, where we hold all other parameters constant and only vary the injection rate and compare a case with constant injection rate as shown by this gray block here to another simulation with periodically periods of injection followed by shut-in. And so what we can see in this figure are the gray blocks that show the different injection histories, and then the colors show the overpressures that are produced from those. So the blue or the cooler colors here represent constant injection rate cases, and then the warmer colors here represent this sort of periodic injection. In this slide and the next couple of slides as well. Okay, and so with this slide, I think I maybe was trying to win an award for figure complexity or something, so I apologize in advance, but bear with me here. So the gray blocks are just those injection histories that I showed on the last slide, so let's just ignore those. And then on the y-axis here, I've plotted 3 properties. So first we have the cumulative number of events in each simulation, and that can be read on the y-axis on the left. Next, with these sort of step functions, we have the cumulative seismic moment release, and that can be read with the outside y-axis on the right. And then at the bottom, we have the individual event magnitudes, and all of these properties are plotted as a function of time. And then the magnitude itself can be read from this smaller y-axis on the inside here on the right. Okay, so what we can see if we compare the results of both of these simulations is that constant injection rates produce a completely different pattern of seismicity, resulting in overall higher number of events. But those events tend to be smaller, as we can see, because the total seismic moment release in this constant injection rate simulations is about half that of the periodic injection. If we look at these same data in a slightly different way, here we're plotting the distance from the injection well to the earthquake as a function of time during the injection simulation. The curves in each of these plots is a simple diffusion profile. There's a couple noticeable features that we'll see here. So first, in constant rate injection, we see that seismicity begins early on and it continues throughout the duration of the injection operation, but with rates sort of decreasing in this period here. And then in comparison for the periodic injection cases, we see these sort of isolated bursts of seismicity, and some of them occurring with large magnitude events in the periods of shut-in. And so this behavior, this sort of clustering or like high rates or bursts of seismicity is very similar to the behavior that Jim showed yesterday for the somewhat simpler rate model. And then finally, we see that there's quite a few events in the post shut-in period here. Some of these events occur when the overpressure on the fault is continues to rise after shut-in, but at larger distances from the injection well. But we'll see most of these events occur on the fault surface as the overpressure is actually decreasing. And so this is the point at which the overpressure returns to about or less than 50% of the maximum pressure. And we see a high density of seismicity in both of these cases. Okay, so with that, just in summary, we've demonstrated the ability to couple geomechanical models with earthquake simulations that are highly efficient. These models produce catalogs of synthetic earthquakes with statistical properties that are similar to observed seismicity, despite making a number of approximations for, say, event nucleation and rupture propagation. And so within the workflow that we've outlined, the computational costs are dominated by the geomechanical simulation, although this will change significantly once we start to incorporate numerical solutions for the earthquake physics. And then finally, I've just included a list here of some of the topics that we can address with these methods. Some of these we've already worked on and others are open research questions. And so with that, I guess we can take questions.
Thanks a lot, Kayla, and thanks, Josh. Great presentations. We have a few questions here from the audience. I guess before working through those, I wonder on a sort of standing back a little, if you compare the predictions of induced seismicity with what is observed and what you know from the injection rates, the production rates. What are the aspects of seismicity that require the full, geomechanical model, that require the knowledge about fault zone orientations and loading stresses? And what are the aspects that can be captured with, say, a homogeneous isotropic stress pulse model that would respond, say, to rate and state friction?
So that's a really good question. I guess I'd have to say, so if you have homogeneous models, at least in the earthquake simulation, you tend to get characteristic ruptures, and the maximum magnitudes of those ruptures tend to be to scale with the fault area, as we see from traditional scaling laws. When you start adding heterogeneity, you can start to do things like limit rupture propagation. And obviously, we know that not every induced earthquake is a characteristic earthquake, at least on the faults that they rupture. So that's, I think, that one of the dominant effects.
I would just also add to that, we know from experience that the details of the reservoir and the permeability and the flow can actually have a very direct impact. So for example, there was a CO2 project which was injecting into a permeable layer relatively close to the basement, generated a fairly high seismic frequency. They moved up just a little bit to put a quite thin but impermeable layer between them and the basement, and saw a reduction in seismic frequency. And so, that sort of detail needs to be in the model if we're going to be able to really understand it. So
right. So we have a bunch of questions. So one is about sort of related. What kind of stress level and what assumptions should be made about faults that have been long dormant, that are considered inactive? Is there something in your modeling experiments where you would have a different estimate of a friction coefficient or fault zone damage compared to an active fault zone? Is there something you can say about that? And then sort of as to the time dependence, there was a question, why do large events occur just after the shut in your simulations?
So these are all very good questions. I think let's see, I'm trying to read the fault maturity question. So yes, fault maturity plays a role. Maybe it plays a role most clearly in the distribution of the stresses along the fault. In a study that is in review right now, we found, for example, if we look at the impact of Mmax, or the maximum magnitude event, on faults with smoother stress fields, this event tends to occur earlier in the start of injection, versus sort of faults that have rougher stress fields tend to delay the onset of that maximum magnitude event. Also, once the event nucleates on a smoother stress field, it's able to propagate more easily than it is on a rougher fault. But there's some limits to that. So if you have really random sort of like high stress asperities, but they're very small high stress asperities, and you have a highly energetic rupture, it can propagate and just blow through that whole entire stress field. These are things I think that we don't fully understand yet, but we certainly have the capabilities to adjust them, and sort of just need some time or some people to help us with that. And then the other question about why do the largest events occur after shut-in? This is not always the case. I sort of cherry-picked an example of where that happens. In the last couple of slides that I showed, I should mention that what we really should do if we want to fully understand the difference between constant injection histories and periodic injection histories, is do the same sets of simulations, but vary all of the properties that we don't know, and look at the full distribution of events. So this is an example, and it doesn't always happen that way. But there's a couple of reasons why maybe in this example it did. First is that the pore fluid pressures may be increasing on the hypocenter of that element, of that rupture that occurs in the shut-in period. If the pressure is increasing there, and also if perhaps it's in a region of high stress, this can cause or lead to a sort of full faulting rupture or a larger event. The second thing is rate and state effects. So Jim talked about these a bunch yesterday. You have these time-dependent nucleation events that are sort of triggered by stress changes from previous events. So in some way they're aftershocks, but the aftershock in this case cascades to a larger event, or maybe even a main shock in some cases. Jim, do you have something to add?
Needed a moment to unmute there. Yeah, so I guess, yeah, the stress level is really kind of a huge unknown. The examples I showed yesterday, I assumed that the initial stresses were at or the seismicity was at a steady state rate, which implies that the stress levels are constant. But of course, it's basically unknown, I think, and it's something that we really need to look at, because you get a stress drop with a nearby earthquake, and suddenly the stress level can change by a huge amount, at least relative to triggering of earthquakes. It's a bit of a mystery to me as to why you would get larger earthquakes during the shut-in period, and I think that's going to be a topic of investigation that we have to look at pretty carefully.
We have two more questions in the Q&A that are interesting. One of them says, thanks for the great talk. What is the longest time scale one can model using the current numerical methods you mentioned? And the person asking is wondering if these models can, in some sense, be coupled with long-term tectonic deformation.
It's a good question. So, yeah, well, the easy answer is that the time steps we take are really being driven by the dynamics of what we're trying to simulate. So if you have an injection well, it's often fluctuating quite quickly. We're taking very small time steps. But there's no reason, and in fact, we do this, that you couldn't take like a time step of 100,000 years. In fact, to initialize the models, sometimes to get to a steady state, we do this artificial simulation where we take huge time steps, 100,000 years for a few million years, just to get to like a steady state that makes sense. The real limitation, I would just say, is that we're solving a certain set of governing equations, and at some point over very long timescales, those will go away. There are people who work on depositional models and geologic timescale models of basin evolution, And those include additional physics that would appear over very, very long time scales. But yeah, if you have if you just want to load a model with a very slow stressing rate and run it for, 100,000 years and take 10,000 year time steps, that would not be hard to do.
Thanks for the answer. There's also a technical one I'm interested to is with which tool did you generate the TED meshes?
Yeah, everyone wants the silver bullet answer, So that mesh was built by a colleague of mine, Antoine Mazuet, who works heavily with the ring mesh consortium. So it's a team that over the years has built up a lot of good tools for these meshing type challenges. I will say that he actually used a series of tools and then a lot of like hand processing. Like you have to go in and clean up a mesh. You generate a mesh and then it's got really distorted cats and you have to clean it up and stuff. So I like to say that he generated it. Yeah, there's certainly good tools out there. It's a subject of active research, but the ring mesh team in that effort would be a good one to look at.
Sort of related to those two questions, given the different spatial scales, and you had also mentioned the challenges of having these different kinds of PDEs involved, have you thought about approaches that have sort of a global time step and a local time step to think about the dealing with these issues?
Well, so certainly the most, yes, I mean, well, so the naive approach, and the one we're kind of working with right now, is you say that we take a very large time steps until we detect that we are about to enter a rupture, and then we transition to very, very small time steps, and then we sequentially go back to very large time steps. I think what you're describing might be a more sophisticated approach where you have embedded like multi-stepping, some equations solved at a certain time scale and other equations and coupling. It is certainly for the multi-phase flow dynamics that's actually frequently used. I didn't show it in my model. Typically, we typically use the same time step for the saturation equations as the mechanics, but there are ways of uncoupling them such that you can take very, very small time steps for the saturation front, do a better job tracking that sort of hyperbolic behavior, and then take large time steps for the near elliptic components. So yeah, so I think there's potential there. We'd have to talk about specifically what and how, but yeah, it's an excellent idea. Similarly in space, multi-scale in space is huge in what we do. So,
do you have time for a last question, Thorsten?
Let's see, do we have something
there?
Yeah, there's a couple more Q&A questions.
So Kadek Pagonadi is asking about the location of the large earthquake for Kayla. Is it related to the distance to the injection well? I mean, how is the location being determined? How does this relate to the distance to the injection well?
Right, so in both of the simulations that I showed, the injection well is about 1,200 meters out of in space away from the fault plane. And the faults in general are modeled to represent basement or to be like sort of geographically within the basement, but the fluids are propagating a lot faster along the fault surface than they would in the basement, so the flow properties are quite different. So it doesn't necessarily get to the question of like if we put an injection well above the basement and it was separated from the basement by a confining layer, whether or not that would cause large earthquakes. So that question is independent of the types of models that we ran, but it's certainly something that we could simulate. One of the primary differences though is the pressure. So what's going to happen, say if you have an infinitely permeable reservoir cut by a fault with also, maybe not infinitely permeable, but with high permeability as well, and you put the injection well farther away from the fault, the pressures on the fault surface are going to decrease. And ultimately, it's the interaction between the pressure and the stress field, both the heterogeneous distribution of the stresses and the overall amplitude of the stress field that's going to cause earthquakes. If we had a very, very small pressure perturbation, say something like kilopascals, and that's applied to a fault that is also, say, a kilopascal away from failure, then you're going to end up with a full faulting rupture. Conversely, if you do the same sort of scenario where you have a fault that's, say, 10 MPa from rupture from failure, then you're not going to do anything, presumably.
Thanks. Yeah, regrettably, we're again a little bit over time, but we have tomorrow. So again, for those in the audience who didn't get their questions answered, our apologies for that. And tomorrow is your chance, hopefully, to bring those up. Appreciate it. So thanks to our speakers, and thanks to Alice and Magali and the panelists for joining again, and thanks to our participants for great questions. This will be recorded. This is recorded. Will be online in a couple of days or so on our webpage. And tomorrow is going to be the last of our series A on induced seismicity and fault systems. So see you tomorrow, and thank you again.
Thanks, everybody.